First, we're going to define the gauge pressure. And the gauge pressure is the product of the density of the liquid, the acceleration due to gravity, which on Earth is going to be 9.81 meters per second squared, and how deep the object is below the surface. That's called the gauge pressure. The pressure does not depend on the total volume of liquid, only the type of liquid, the acceleration due to gravity, and the depth. The P in the equation P equals rho GH, that is the gauge pressure, does not account for the pressure at the liquid's surface from gases above it. To find the total pressure at a given depth, simply add the surface pressure, which I'm going to call P naught, to the gauge pressure at that depth. In other words, the total pressure equation is the gauge pressure, rho GH, plus the surface pressure, P naught. So let's explain this a little further. Here we have a liquid, and we're showing that that's the surface using that funny symbol on the right there. The atmosphere pushes on that liquid with a certain pressure. We're going to call that the surface pressure. Within the liquid, at a certain depth below the surface, there is a gauge pressure due to that depth. There's a certain gauge pressure at this depth, a bigger one at this depth, and bigger, and bigger, and bigger. So, the red arrows indicate the surface pressure. The gauge pressure is indicated by the blue arrows. The surface pressure is constant at that location, and the gauge pressure depends on the depth. So the total pressure at any particular point is due to the sum of the surface pressure, which is constant, and the gauge pressure, which depends on how deep you are. Let's do a problem. Given that the specific gravity of gasoline is 0.68, find both the gauge and total pressures 1.4 meters below the surface of a tank of gasoline that has airspace at the top. Assume the air pressure to be 101.3 kilopascals. Let's find the gauge pressure first, rho GH. The specific gravity is 0.68. So we can find the density of gasoline by taking 0.68 times 1,000. Remember that the specific gravity is the ratio of the density of, in this case, gasoline to the density of water. Well, the density of water is 1,000. So if the specific gravity is 0.68, that must mean that the density of gasoline is 680 kilograms per cubic meter. G is 9.81. We're going to assume that we're on Earth unless we're told otherwise. And the depth is 1.4 meters below the surface, so the gauge pressure is about 9,300 pascals, which is equal to 9.3 kilopascals. I trust you could make that conversion. The total pressure then is the sum of the gauge pressure and the surface pressure. Well, the surface pressure, which is the air pressure, which is given as 101.3 kilopascals, there's the gauge pressure that we just calculated. The sum of those should be the total pressure. And there you go. Do the same calculations if we're 2.8 meters below the surface of the gasoline instead of 1.4. The gauge pressure will be 18.7 kilopascals. 680 times 9.81 times 2.8. That's 18.7. The total pressure, then, we must add in the surface pressure, which is 101.3, about 120 kilopascals. Let's summarize. The gauge pressure P is the pressure from just a liquid, and that's found using this equation in yellow on the right, rho GH. The total pressure is the gauge pressure plus the pressure from any gas above the liquid, and that's this equation, P naught plus rho GH. The gauge pressure depends on a liquid's density, rho, the acceleration due to gravity, g, and the depth below the surface. It does not depend on the volume of the liquid or the shape of the container.